Okay, so hello and welcome. Howdy. Here we are. Another question. Let's give it a moment to make sure the audio is working. This is number. Hello. Let's give it a moment. This is number 1123, the lowest common ancestor of deepest leaves. And we'll begin. So, lowest common ancestor of deepest leaves. Given the root of a binary tree, return the lowest common ancestor of its deepest leaves. I think I've done this question before. I think I've seen it before. Recall that the node of a binary tree is a leaf if and only if it has no children. The depth of the root of the tree is 0 if the depth of a node is d. The depth of each of its children is d plus 1. The lowest common ancestor of a set S of nodes is the node A with the largest depth, such that every node in S is in the subtree with the root A. Yeah, so basically, I think what I want is I can calculate the depth of each node using a DFS, and then I can also calculate the greatest depth of any of the children of the node, the greatest depth of all the ancestors of that node. And the deepest one, the lowest common ancestor, is going to be of all the nodes with the deepest depth, right, the deepest, max depth. The one with the least depth is the one that I'm looking for. Yeah, pretty interesting. Yeah, so I probably just want to find the greatest depth first to start with, number one. Then I want two things. I want to know for each node, I want to know its the node values are between 0 and 1,000. The number of nodes are between 1 and 1,000. The values of the nodes are unique. This question is the same as 865. Okay. Yeah, relatively high submission rate and high acceptance rate. Reasonable submission rate or high acceptance rate. I forgot how I did this the first time, but I think I did something similar. Yeah, it's the same question. I was gonna say I did this before. I don't remember how I did it last time, but I think I'm pretty sure I did something similar. You can. Okay, I think the thing to do is first find the greatest depth. Start with that. So one pass to find the depth, greatest depth. The next path is for each node find its depth and the depth of the greatest depth of all of its ancestors. And if it has the depth of all of its ancestors, if that's equal to the greatest depth, then compare that node to the node with the that also has the same subtree of depths, and get the smallest one. Yeah, the smallest. It's the lowest common ancestor, excuse me. It's the one with the greatest depth that has that depth. Yeah, excuse me. Yeah, it's the greatest depth. Right. I'm sorry, it's the one that has the greatest depth where both children have that max depth. Actually, I'm making mistakes here. I'm not thinking that through. I don't know. If both subtrees don't have the greatest depth, then you can go to you can do it that way. That's how I did it the first time. Actually, it's a pretty good way of doing it. You basically stop when both subtrees have the greatest depth. when all of the yeah. You want the depth that's highest, that's the furthest down where that's true. No, actually, you want the smallest depth where that's true. So, and you could stop too when you find that. You don't need to go deeper into the subtrees. Yeah. Can even just do left and right. It's, well, I'm trying to think of a way to do this that doesn't use extra memory. I think the first time I did it, I used extra memory. One pass can get you the greatest depth. Two passes, you can figure out what the I guess there's extra memory with regard to like traversing the tree, the stack, but more memory beyond the stack, I guess what I'm referring to. Yeah, you could do a depth first search just to get the greatest depth, and then you could also do another depth first search that figures out what the greatest depth the depth of the node is and the greatest depth of the ancestors of that node. I guess you could do it all in tandem, actually. No, you can't. You got to do two passes, I think. Yeah, two passes is fine. The second pass, now you're finding the depth of the node, and comparing it to the and its children, the depth of the children, and is that right? That's kind of confusing. Yeah, that's fine. Two DFSs is fine. Yeah, two DFS is fine. Okay. And so if the left child and the right child, if the all of the children, if the max depth of the subtree is they're both equal to the maximum depth of the whole tree, which it is in this case, right? Or no, it's not in this case. This one isn't. If both children are, then that means this node itself also is, and it also means that that's potentially an LCA of the deepest leaves, but it is an LCA of the deepest leaves, but it's not necessarily the lowest. This one's not, but this one is. These are both, their subtree contains deepest leaves, but it's not necessarily the least such. Yeah. Yeah, it's kind of confusing. Why would it have to? It has to be both children to be considered. Why? Because this actually contains all of the deepest subtrees, deepest leaves. It's just not the lowest one. How do I know it contains all of them? Well, the root node does. This one does. This one doesn't. Um, Yeah, if both subtrees don't contain deepest leaves, then it's clear that that node could be discarded, right? From consideration. Interestingly, the lowest common ancestor with the deepest leaves, with all the deepest leaves, is also the greatest ancestor for which the the least depth ancestor. So this is the greatest depth ancestor that contains all of them. Is also the lowest depth ancestor, lowest depth node that contains a left child and a right child with deepest leaves. Yes, because any other node that contains deepest leaves in the left side or the right side. First off, any node that contains deepest leaves on the left side but not the right side, or vice versa, only one side, that doesn't contain all the deepest leaves. Or no, that doesn't. You don't need to look at the leaves on. You can go to a lower point, right? That may contain all of the deepest leaves, but you could go to a lower point. And then of those nodes where it's guaranteed to have deepest leaves on the left side and the right side, you may be able to go higher because you may be missing some leaves. The highest point where that's true is guaranteed to be. Yeah, it's a pretty interesting question. I figured it out very quickly last time, but this time around I'm kind of like, well, wait a minute. Wait a second here. Wait a second. Excuse me. um. Yeah, no kidding. Sure. We'll call it the target node that we're looking for, right? We'll call it the target node. The target node, it's going to be at a lower depth than any of the nodes that are that have one subtree that contains the max depth, the deepest deepest leaves, and another subtree that doesn't contain any deepest leaves. That the target's going to have a lower depth than those nodes. We can ignore those nodes. However, of the nodes that do have on the left subtree some deepest leaves and the right subtree the deepest leaves, the node with the highest such depth that has that property is the target. And the reason is that it's possible that any of those particular nodes could be missing some deepest leaves, so you may have to go up. However, if you go too far up, then you'll start to include subtrees that don't have any deepest leaves, which is exactly what I tossed out before. So going far enough up to stop at that point, but also going above all of the nodes that have a left subtree and a right subtree that both contain deepest leaves. That's the target. Because that has a lower depth has the lower depth and has the lowest depth, and it's the one with the lowest depth the one with the lowest depth is guaranteed to have all the leaves. Whereas if you take a depth that goes down further, a greater depth, then you would necessarily be excluding. Almost by definition, you'd be excluding some of the deepest leaves. Yes. Yes, so that's pretty interesting. That's pretty interesting. So we're looking for the node with the, is it highest depth, lowest depth? The node with the lowest depth that also is in that category where it has a left subtree with the deepest leaves and a right subtree with deepest leaves. That's the node I want. Yes. Yes. Alrighty. So tree node result, return result. We're going to DFS int deepest greatest depth or G depth. Start off at 0. DFS1. The first DFS is just going to get the first DFS is just going to get the it's just going to get the greatest depth. So start off at 0 and return D. So if node and not node left and not node right, return D. So if it's just one node, we have a depth of 0. If it's like a node on the left, node on the right, then we would say this should never really be reached. Well, yeah, okay, that's fine. No. Node on the left, node on the right. We would say the depth is increment by 1. Right? And then it's a leaf node, so we would just return 1. But let's say it wasn't a leaf node. Let's say we had a node on the left and no node on the right. I want left and right. And I want to return not sure if that makes sense. So the greatest depth of the left side, greatest depth of the right side, which is 1 and 1. The return value I'm going to have is 2. Okay. Interesting. This is a little bit confusing. This is a little bit confusing. I think I return 0 here. Yeah, this is a strange thing. It's actually just the left side and the right side. I don't need the depth D initially. I don't even need that. I was gonna say it's not necessary. Yeah. So the greatest depth for each node, that's what this is gonna get. It's just the greatest depth. Gonna find the greatest depth of the left side, greatest depth of the right side, and add 1 to it at the root node, right? And then the greatest depth of a subtree that's empty is just 0. Really should be -1, I think, actually. But 0 is fine. 0 could just mean no nodes. Okay, so we do that. That works. That's fine. Now DFS2 is a little more involved. this is going to say gdepth node d is the current depth of the node. Now again, I'm going to calculate the maximum depth. Excuse me. At each node, right? And we're going to say this is the result int return or ret value. I'll say return value. And I'm going to say now the current depth d plus 1, right? Maybe this current depth should be a 1 initially. Kind of conflicted about that. Empty subtree has a depth of 0. Okay, so the depth first node is going to be d0. Yeah, let's do 1. Okay, we could start this off as the root. That's fine. Now, what we're going to say is if we have best depth, b depth is 0. Yeah. Depth of the root really should be 0, I think, or 1. Yeah, 1. Let me, there's always at least one node. Okay, I was gonna say I should handle that. I can handle that case where the root is not as null pointer, but that actually doesn't matter. All right, so never mind. This is wrong. Actually, I don't want to do it that way. Null pointer 0 is what I want first. This should actually be e to the 4th. Okay. So if the current depth, which is going to start off at 1, if that is less than the b depth, and the left side is equal to g depth, and the right side is equal to g depth, then I can update b depth equal to d and results equal to node. It's something like this. Yeah. Because the left side and the right side, their maximum depths are as deep as possible. This is wrong. Oh man, I'm so confused. I don't know what's going on here. Maybe I need some sleep or something. I'm kind of doing this pretty slowly. Maybe I should try to use memory for this. It's like it's a little bit awkward if I don't use any memory. It's hard to like keep track of what's what. This gives me the maximum depth, but it's not quite right. It's yeah, it's the maximum depth of that particular subtree, right? And I can use that to get the max depth, the greatest depth. And this gives me let's say it's like 1, 1, 2, 3 is the tree, right? The maximum depth should be 2. Yeah, that's correct. Okay. So you've got trees at max depth 2. That's fine. But leaves at max depth 2. Now, what's interesting about this is that this is, what is this left and right return? Now, this is slightly different. This is going to give me the maximum depth of any nodes that I see, which should be actually which is a little more complicated. So this should return D. Yeah, so now we have 1, 2, 3. This should give me left and right. Okay. So I return D as I go down. So D starts off at 1. Then recurse on the left side and right side with 2 and 2. Then left and right again, we get 3 and 3. Both of those return 3. Yeah, that's actually not quite what I want. It's more like not node and not node left and not node right. This should return D, right? The leaf node should return D. If it's not a leaf node though, then yeah, return D minus 1 I think is fine. Just doesn't change. In which case this is fine, actually. Yeah, this is just we're gonna add 1 and then subtract 1 again. I think it's okay. I think it's fine. But now this return value is gonna be the larger of the two, right? Let's say my left subtree goes a little bit deeper, right? Let's say it goes 2 more nodes deeper, and I get, so we have a 1, and then the left side has 2, 3, and 3, and so that second node where 2 was, that's actually going to return 3, right? The 3 and 3, it's going to return 3. On the right side, that's going to return 2, but now my root node is going to be also have a 3. Okay. Now, if the left and right side both have the greatest depth of 3, and my current depth, which would be a 1, is less than the best depth, which is a sentinel value initially, I got to update my result to this particular node and update the depth. It's something like this. It's a bit complicated, quite frankly, but I think it's something along these lines works. Oh, got it. 1, 2, 3, 4, 5. Okay. I did the same mistake twice. 1, 2, 3, 4, 5. Wait, I don't need the 0 here. Yeah, going through this pretty slow. Oh, this returns RT as well. Forgot about that. Oh, it worked. Cool. Yeah, a little bit confusing, but the depth is correct, right? Depth is 0 at the bottom, and then so if it goes, yes, that's correct. Okay, I'm gonna go for it. Just gonna go for it. I could be wrong, but I think it's right. It's good. Okay. All right. That took like half an hour. That took a while. That's pretty fast. Pretty fast. Didn't use that much memory. We're gonna submit it 4 more times. I've solved this question before, but I definitely. It's kind of challenging. It's tricky. Trying to not use that much extra memory is challenging. This is fast enough. I think this is relatively fast. We'll submit it 2 more times, and then I'll say, excuse me. Thank you for watching. It is actually a little bit of extra memory because of the stack. But I like this. I like this approach. 2 pass approach is fun. So yeah, thanks for watching. I will talk to you soon. I'm going to submit it 1 more time just to see if I can get it a little bit faster. And if you like the video, give it a like and subscribe for more. If you like this content, if you want more of the content, subscribe. Yeah, subscribe for more videos like this. So yeah, like the video, and subscribe for more content like this. And I think that's it for me for this question. That's not it for me for today. I'm going to go ahead and restart the stream on another question, but that's it for this one. Yeah, this one, I've done it before. It's not too hard, not too bad. You could do it fairly quickly, I think, but I wanted to kind of think it through a little bit more and think about, like, how could I do this without necessarily having like a hash map or an array of values for the nodes, or just kind of do it like without any extra memory beyond the stack. And this was a 2-pass solution. This is pretty good. This is reasonable. I think the last one was a 2-pass solution anyway that I did. So yeah, thank you for watching.